Hello everyone, welcome to our second chapter since we've been away. I hope that you all are doing well and I hope that you're able to learn this material. This is chapter 26, which is about refraction. Now remember that the light can have three things happen to it when it strikes a surface. It can be reflected, which we've talked about. It can be absorbed, which we've talked about in terms of internal energy, or it can be retransmitted. When it's retransmitted, it is either transparency, which we've talked about, or refraction. And that's what this chapter is about. So we're going to talk about refraction and how it can be used, say, in lenses and optical instruments and such. I've divided this PowerPoint into two parts to make it a little easier. I've also given you the study guide both with and without answers. What I would recommend doing to help you learn the material is fill it out as you're going, and then when you're all done, go back to the one with the answers and check. Now, I can't make you do that, but that will help you learn it the best. So I hope everyone's doing well, and with that said, let's continue. For this chapter, we're going to describe refraction, like I said. We're going to talk about total internal reflection, which is when the refraction is so great that no light passes through. And then in the second half, I'll talk about polarization and more ray diagrams, similar to what we did for mirrors. So to start, let's talk about light. And what do I mean by refraction and something called the index of refraction? Well, light travels through a vacuum at a speed of 3 times 10 to the 8th, as we talked about before. That's rounded up a little bit. It's 2.9998 or 998, but 3.00 times 10 to the 8th is pretty close. But that's in a vacuum. It travels through other materials, or really any material, at a speed less than that, because even light interacts with things, and that slows it down. So this change in speed causes a change in direction. And that's what refraction is, a change in speed causing a change in direction of electromagnetic radiation. Now, how do we know how much bending or changing in direction is going to happen? Well, we know that through something called the index of refraction. And that's basically just where you experimentally determine what the speed of light is in that material. And then you take the ratio of the speed of light in a vacuum to the speed of light in that material. And that's your index of refraction, which will always be a number greater than 1 because V has to be smaller than C. Here's some examples of some indices of refraction. We see that in air, it's really close to 1. So that's why we generally just say 3 times 10 to the 8th even when we're in air, because it's close. But in water, you'll see a significant difference, 1.333. And if you go to a diamond, 2.419, that's a huge index of refraction, which is one reason why diamonds sparkle, because the higher the index of refraction is, the more total internal reflection there will be, which we'll talk about before, which means once the light gets into the diamond, it takes it a while to get back out because it just bounces around inside. Now, if we're going to bend light as it goes from one material to another, and we have these indices of refraction, how can we use them to determine how much light will be bent when it travels? So when light travels from a material with one index of refraction to a material with a different index of refraction, we can use Snell's law to determine the amount of refraction. Snell's law says that when light travels from a material with one index of refraction to a material with a different index of refraction, the angle of incidence, theta 1, is related to the angle of refraction, theta 2, by the equation N1, the first indices of refraction, times the sine of the angle it makes with the normal, equals N2 times the sine of the angle it makes to the normal. So if you look at the diagrams, you'll see that you have an incident and a reflected ray. Remember, some light is reflected, some of it is refracted. On a mirror, most of it's reflected. In water, only like 3 to 10% is reflected. That's why you can see a reflection in water, but you can also see through water. Now we know from the law of reflection that theta 1 and theta 1 are the same, and incident angle and reflected angle are the same. But notice how the refracted angle, theta 2, is different. Now when you slow down, when you go from air to water, you slow down, you bend towards the normal. And if you go in the reverse direction, let's say that the light is actually in the water so that it shines upward into the air. In this case, it's speeding up. It's going from a slower material to a faster material. And notice how the light bends away. It bends away from the normal. So towards the normal when it slows down, away from the normal when it speeds up. And light can go in both directions there. Let's look at an example. A light ray strikes an air-water surface at an angle of 46 degrees. So we have two situations though. It can go from the air to the water, or it can go from the water to the air. How can I find that index of refraction? Well, we have two cases here. The first is when the upper theta is 46 degrees. And if I solve Snell's law for theta, sine of theta 2, I see sine of theta 2 equals n1 sine of theta 1 divided by n2. In this case, n1 is 1 and n2 is 1.33. I put those into the equation. I get 0.54. I take the arc sine of that and I get 33 degrees. So it was 46, now it's 33. It bent towards the normal because it slowed down. Now if I switch it around so that n1 is now 1.33 and n2 is now 1, I get a sine of the angle equal to 0.96 or an angle of 74 degrees. It bent away from the normal in the reverse reaction. So that's just applying Snell's law to see how much or what the angle will be when you know both indices of refraction and one of the angles, usually the incident angle. Now notice how it bends towards, when you go from air to water, it bends towards the normal. This can affect a lot of things, like let's say you're trying to catch fish. Well, the fish is going to appear to be farther away than it actually is because your eyeball, it will trace that incident ray into the water as a straight line. Your eye doesn't know itself that that ray has been refracted down. Your brain has to tell it that. So if you're ever spearfishing, you always have to aim closer than the object you see because that's where the object actually is. But your brain can make that computation. Your eyeball can't. So let's look at an example dealing with depth. Finding a sunken chest. A searchlight on a yacht is being used to illuminate a sunken chest. At what angle of incident should the light be aimed? Notice that the light actually has to be aimed away from the chest in order to illuminate the chest. So let's say that that chest is 2 meters away from where the light strikes and it's 3.3 meters deep. I can use that to trigonometrically solve for theta 2. And I know n1 and n2. And that allows me to solve for theta 1. So theta 2 has to be the arctan of 2 over 3.3 or 31 degrees. But theta 1 from Snell's law has to be 44 degrees because that light is going to bend towards. So for me to illuminate that chest for the divers, I need that angle to be 44 degrees. Now, interestingly here, look at this kind of talks about what I was talking about before. Your eye thinks that the chest is like at a farther angle than you. It seems farther away, but it also seems less deep. So if you look at diagram A, see how your eye traces those light rays straight back. So pick 2 rays. Each one of them goes from your eye to the water and then bends down. Your eye traces those straight back, and it creates an apparent depth where the unrefracted light would go. And we can actually solve that apparent depth. D prime is equal to D divided by the ratio of the indices of refraction. So the ratio of indices of refraction will also affect apparent depth. So the apparent depth is equal to the actual depth times the ratio of the indices of refraction. So if I gave you both indices of refraction, and usually you know the apparent depth, you can calculate the actual depth. Or if you know the actual depth, you can calculate the apparent depth. So let's look at a conceptually example. A swimmer is underwater and looking up at the surface. Someone holds a coin in the air directly above the swimmer's eye. To the swimmer, the coin appears to be at a certain height above the water. Is the apparent height of the coin greater than, less than, or the same? Now don't look ahead. Think about that. Remember, N2 in air, in this case, is now smaller than N1. So in this case, the coin will appear closer than it actually is. So everything always appears to be different in sizes. Or, sorry, distances in this case. So when light passes from a media of larger refractive index into one of smaller refractive index, the ray bends away from the normal, right? So here we're pretend the light is back in the water so that we're bending away as we go out into the air. So notice that it bends away. So the refracted ray is always going to be at a greater angle. That means that there will be an angle called the critical angle where that refracted light will actually lie along the surface. And if I go greater than that critical angle, there's no more refraction because all of the light becomes reflected. Nothing can be refracted anymore because it bends back into the water, which causes it to be completely reflected. Now that critical angle, it turns out, has a value that you can determine by the sine. So the sine of that critical angle will equal the ratio of these indices of refraction. See how useful these indices of refractions are? The sine of the angle is equal to the index of refraction of the surface you're going into divided by the surface you're coming out of. So you want that sine theta c. Notice how this will only work if n2 is smaller than n1. So you have to be bending away from the normal. If you go the other way, you're not going to get a critical angle at all. Another example of this, as you can see, when I talked about a Marquis cut of a diamond, a beam of light is propagating through a diamond, and it strikes the diamond-air interface at an angle of incidence of 28 degrees. Will part of the beam enter the air, or will there be total internal reflection? Then we can repeat it, assuming that the diamond is surrounded by water. Now water has a higher index of refraction than light. So it could be internally reflected in air and not internally reflected in water because the difference in indices of refraction is not as great. So that theta c would be the arc sine of the ratio of the indices of refraction. If I do that going from between air and the diamond, 1 and 2.42, I see a 24.4 degree angle of incidence. If I did it with water, which is 1.33 indice of refraction, I see a 33.3 degree angle. So if I am between 24.4 and 33.3 degrees, it would be internally reflected for air, but not for water because water hasn't hit the critical angle yet. Now, the diamond is famous for its sparkle because the light coming in glitters as you move it about. Why does it exhibit such brilliance? Well, the reason for that is as you move it around, certain angles cause internal reflection, which makes it sparkle, and then you get to a different angle where you're below the critical angle and you get pass through. So why does it lose much of its brilliance when placed under water? Well, with water, there's less internal reflection, so it doesn't bounce around inside as much. So in the air, it bounces around inside more because it has a smaller critical angle. And you can get a lot of sparkling depending upon how you move the diamond around. Now this is one thing that fiber optics make use of because the angle of incidence is always greater than is necessary. It's always beyond the critical angle, which allows the light to propagate down the wire. Now some of it is going to be absorbed by the cladding, which makes it kind of glow. So you do lose some intensity as you go, but not enough to matter, and the light can travel down the fiber optics. Now there is one special angle of incidence. So we already talked about the critical angle, but there's another angle called Brewster's angle. That's a special angle where the angle of incidence at which the reflected light is completely polarized parallel to the surface. And the refracted ray is partially polarized, by the way, not completely. But at this angle, Brewster's angle, the reflected light is polarized. Now, the reflected light will always be partially polarized. I've talked about that before, like with using polarized glasses while driving. But there's one angle where it'll be completely polarized. And I should say also partially polarizing the refracted light. And it turns out that this angle is related to the tangent. So the tangent of the angle of incidence will equal, or when the tangent of the angle of incidence equals the ratio of the indices of refractions, you get completely polarized reflected light. So tangent determines Brewster's angle, and that gives you polarization effect. Now, another way that we can make use of the bending of light is with the prisms, because prisms change the direction of a light ray. And since different light colors are all present simultaneously, so light coming from the sun has all of the different wavelengths of light in it. But when that light strikes a surface that changes the speed of light, it will affect the speed of light differently for different wavelengths. And because of that, different wavelengths get refracted differently. So light rays corresponding to different colors bend by different amounts because the refractive index of glass is dependent upon wavelength. Different wavelengths will bend differently. Think about it this way. You have a huge cylinder rolling, and that huge cylinder hits a piece of grass. It's rolling down a concrete sidewalk, and it hits grass, and that grass causes it to turn. But once all of the roller is in the grass, it will go straight. Now, if I take a much smaller roller and roll it down the concrete and it hits the grass, it's not going to turn as much because it will all enter the grass faster. So a longer tube will hit the grass on one edge first and start to turn. As it keeps going into the grass, it will eventually all be in the grass, but in the meantime, it's turned. A smaller tube will enter the grass faster and therefore will not turn as much. And if you look here, notice how red has a smaller wavelength, a larger wavelength than violet. So the grass is just kind of an example to show you that things bend differently based upon length. Now, red light, which has a smaller wavelength, which means a larger wavelength, will bend actually less. So it's not the best example, but it does kind of conceptually help you understand why things would curve differently. But here you can see red and violet will bend differently at each interface. So when they go from air to glass, they bend. And then when they go from glass to air, they bend again. And this is what causes the light to separate. And if you ever do want to play with the prism, notice the angle that the incident ray is hitting the glass. People always have trouble figuring out where to place a prism with respect to the light in order to get a good rainbow, and that angle's a really good one there. Now, a good one to use is crown glass. Plastic is not as good, but as you can see that different colors have different indices of refraction. Every wavelength of electromagnetic light has a different indice of refraction. So when we're talking about light and we're talking about different indices of refraction, we usually take an average of all of the different colors of light and just give you one indice of refraction. But in reality, every time you take non-coherent, multicolored light and it hits a surface, it's going to be separated at least somewhat, which is why we tend to do all of these refractions experiments with lasers that are coherent and a single wavelength, so we don't need to worry about that. So what I'm trying to say is everything that I've talked about before, we were using a single index of refraction for light. But what I'm trying to tell you here is that in actuality, every wavelength of light within that, every photon within that will have a slightly different indice of refraction. So what you should know now is that the refraction of light depends on two refractive indices, what you're coming from and what you're going to. It is possible for a prism to bend light upward, downward, or not at all, for instance. And the difference is because it's not just the prism that matters, but it's the other material. So for instance, if a prism is immersed in a fluid with a larger refractive index than the glass, you get situation A, where it just ends up bending towards the normal, right? If you look at A, initially there's a large angle of incidence, but when it leaves, there's a very small angle of incidence. You've bent it towards. With the air and glass, it was actually bending away. It was bending the light away. But if I switched it and I used a fluid with a larger index of refraction, so I can't go back without messing up the recording, but in air has an index of refraction of 1, and this type of glass is 1.5. So it's going to bend away. But if I put it in a fluid with an index of refraction, say, of 2, now the outside is greater, so it's going to bend. It's going to go from greater to smaller in that case. So it'll have the opposite effect. Now, if they have the same index of refraction, it will pass straight through with no bending. And that's how magicians do like the walking on water trick. They use their special plastics that have the same index of refraction as water. And because of that, these plastics are literally invisible. You can't see them in the water because they are completely transparent in water. So I hope that makes sense. You can go back through the PowerPoint a couple of times to understand that how the index of refractions are changing, whether it bends towards the normal or away from the normal, or if they're the same, it doesn't bend at all. And of course, refraction is one of the reasons why we get rainbows, because you get light that comes in with all the colors of light in it. It gets bent around in the water droplets. So when you have a mist, like if you ever spray your hose, your garden hose, so that it creates a fine mist, that's one way to create a rainbow. And that's simply because of refraction. And I think that's the last slide. I could be wrong. Oh, I got a couple more. Yeah, this one I don't think was supposed to be in this slide, but I thought this one was supposed to be the next one, but I will go ahead and talk about it. Another term is chromatic aberration, and this arises when different colors are focused at different points along a principal axis. All that means is if you have light that bends differently with a lens, each color of light will have a different focal point. And I'm going to talk about lenses and their focal points later, but it relates to mirrors having a focal point. But with lenses, every wavelength of light will have a different focal point. And there are ways to correct that. As you can see in part B, you can fix chromatic aberration by having multiple lenses together. If you have both a convex and a diverging and a converging lens both, you can cancel out their effects. Basically, it's like having a piece of flat glass.